far above the clouds of Venus, hidden beneath one of the most hostile atmospheres in the solar system, lies a landscape unlike anything found on any other planet. A strange, chaotic terrain of ridges and valleys, twisted and folded as if the planet itself had once been slowly crushed and reshaped from within. Scientists call it Tessera terrain. These regions appear as vast networks of intersecting ridges and fractured plateaus, covering parts of Venus like a giant geological puzzle. Unlike the smoother volcanic plains that dominate most of the planet, Tessera terrain looks older, more complex, and far more mysterious. Some scientists believe these landscapes may preserve the oldest surface on Venus, a record of ancient tectonic forces that once reshaped the entire planet. Others think they may reveal clues about how Venus evolved into the scorching world we see today. But despite decades of study, the origin of Tessera terrain remains one of the greatest unsolved mysteries in planetary science. If you enjoy calm journeys through the mysteries of space, consider subscribing to Theories Before Sleep. Tonight, we travel to Earth's mysterious twin to uncover the puzzle of Venus's Tessera terrain. From space, Venus appears almost peaceful. It shines brightly in our sky, often called Earth's twin because of its similar size and mass. To ancient observers, it looked like a beautiful morning or evening star, a steady light rising before sunrise or glowing softly after sunset. But beneath its glowing clouds lies one of the most extreme environments in the solar system. Venus is a world of crushing pressure, searing heat, and a dense atmosphere that hides the surface from view. Temperatures on Venus reach around 465 degrees Celsius, hot enough to melt lead. The pressure at the surface is more than 90 times greater than Earth's, similar to the pressure nearly a kilometer beneath the ocean. Even spacecraft struggle to survive there. When the first probes landed on Venus during the 20th century, they transmitted images and data for only a short time before the extreme environment destroyed them. The Soviet landers that reached the surface managed to survive for less than 2 hours. And yet, those brief moments revealed something extraordinary. Beneath the thick clouds of Venus lies a world shaped by volcanoes, massive lava plains, towering mountains, and strange geological formations unlike anything found on Earth. Among the most mysterious of these formations are regions known as Tessera terrain. These landscapes look chaotic from orbit, vast plateaus crisscrossed by ridges and valleys that intersect at strange angles. Instead of the smoother volcanic plains that dominate most of Venus, Tessera regions appear wrinkled and fractured, almost as if the planet's crust had once been folded and crushed repeatedly. Scientists gave them the name Tessera because the terrain resembles a mosaic of broken pieces, like tiles arranged in a complex pattern. But these strange regions are more than just unusual landscapes. They may hold the key to understanding the deep history of Venus, because many researchers believe that Tessera terrain represents the oldest surviving surface on the planet. To understand why that matters, we need to look at how planetary surfaces evolve over time. On Earth, the surface of our planet is constantly changing. Plate tectonics slowly recycles the crust, pushing continents apart, forming mountains, and dragging older rocks deep into the mantle. Because of this constant recycling, very little of Earth's original crust remains. Most of our planet's surface is relatively young in geological terms. Venus, however, appears to operate differently. For a long time, scientists believed Venus had no plate tectonics like Earth. Instead of moving crustal plates, the planet may experience long periods of stability interrupted by enormous volcanic resurfacing events. These events could cover vast regions with lava, effectively resetting the surface. If this is true, then much of Venus's visible terrain may have formed during a relatively recent geological event, perhaps 500 to 700 million years ago. But Tessera terrain seems different. When radar images from orbiting spacecraft revealed these regions, scientists immediately noticed something unusual. Tessera landscapes appear much more heavily deformed than surrounding areas. They contain intersecting ridges, valleys, and folds that run in multiple directions, suggesting that the crust in these areas experienced intense tectonic forces long ago. Even more importantly, volcanic plains often appear to flow around Tessera regions rather than covering them. This suggests that the Tessera terrain may already have existed before the massive lava flows that reshaped much of the planet. In other words, these regions could be fragments of ancient Venus, remnants of a much older surface that survived later geological activity. But if Tessera terrain really is ancient, it raises an important question. What kind of processes could have created such complex landscapes? To answer that, scientists needed better observations of Venus. Unfortunately, studying the surface of Venus is extremely difficult. The planet is permanently covered by thick clouds made primarily of sulfuric acid droplets. These clouds reflect most visible light, making it impossible to see the surface with ordinary telescopes. Even spacecraft orbiting Venus cannot observe the ground using traditional cameras. Instead, scientists rely on radar imaging. Radar works by sending radio waves through the atmosphere toward the surface. These waves bounce back to the spacecraft, allowing scientists to reconstruct detailed maps of the terrain. One of the most important missions to map Venus in this way was Magellan. Launched by NASA in 1989, Magellan spent several years orbiting Venus and using radar to map nearly the entire surface of the planet. The images it returned transformed our understanding of Venus. For the first time, scientists could see the mountains, valleys, lava flows, and impact craters scattered across the planet. And among these features, Tessera terrain stood out immediately. The radar images revealed regions with incredibly complex structures, ridges crossing ridges, valleys intersecting valleys, and patterns that looked almost like woven fabric stretched across the surface. Some Tessera regions extend for hundreds of kilometers. Others rise high above the surrounding plains, forming rugged plateaus that appear far older and more deformed than anything nearby. One of the largest Tessera regions lies within an area known as Aphrodite Terra. This massive highland stretches thousands of kilometers across Venus's surface and contains some of the most complex tectonic features ever observed on another planet. Within these regions, the crust appears to have been squeezed, stretched, folded, and fractured repeatedly. Some ridges run parallel for hundreds of kilometers. Others intersect at sharp angles, forming diamond-shaped patterns that give the terrain its mosaic-like appearance. But what makes Tessera terrain especially puzzling is the sequence of deformation recorded in the rocks. The intersecting ridges suggest that the crust was compressed from multiple directions at different times. This means the surface was not shaped by a single event. Instead, it experienced a long and complicated geological history. For planetary scientists, this is extremely exciting because it suggests that Venus may once have had a far more dynamic tectonic system than we see today, perhaps something closer to Earth's plate tectonics, or perhaps something entirely different. Understanding Tessera terrain could therefore reveal how Venus evolved from its ancient past into the extreme world we observe today. But the mystery does not end there. Another strange feature of Tessera terrain is its elevation. Many Tessera regions sit higher than the surrounding volcanic plains. This suggests that the crust in these areas may be thicker or stronger than elsewhere on the planet. In some cases, Tessera plateaus appear to have resisted burial by lava flows that covered neighboring regions. This raises another intriguing possibility. Maybe Tessera terrain represents fragments of a different type of crust, perhaps similar to Earth's continents. On Earth, continental crust is thicker and less dense than oceanic crust. Because of this, continents tend to remain elevated and survive longer than other parts of the planet's surface. Some scientists have suggested that Tessera terrain might be the closest thing Venus has to continents. If that idea is correct, then these strange plateaus could preserve clues about ancient geological processes that no longer operate on Venus today. But proving this is extremely difficult. The thick atmosphere of Venus prevents us from directly sampling the rocks that form Tessera terrain. Without physical samples, scientists must rely on indirect evidence from radar images and gravitational measurements. Even so, the patterns seen in these images provide important hints. The intersecting ridges and folds resemble structures formed by compression in Earth's crust. When tectonic plates collide on Earth, rocks are pushed upward and folded into mountain ranges. Similar processes could have occurred on Venus long ago. But Venus does not appear to have active plate tectonics today. So if these structures formed through tectonic forces, those forces must have been part of an earlier geological era, an era that may have ended hundreds of millions of years ago. In this sense, Tessera terrain may be like a fossil record of ancient Venus, a preserved snapshot of geological activity that once shaped the entire planet. And because these regions survived later volcanic resurfacing, they may hold the only clues we have about that ancient world. But many questions remain. How exactly did these ridges and valleys form? What kind of forces could have deformed the crust so intensely? Did Venus once have a tectonic system similar to Earth's? Or were these structures created by a completely different type of planetary process? To answer these questions, scientists continue to analyze the data collected by missions like Magellan and develop new models of Venus's interior. Future spacecraft may eventually provide even more detailed maps of these mysterious regions, and perhaps one day landers will reach the Tessera terrain itself, allowing scientists to study its rocks directly. Until then, Tessera terrain remains one of the greatest geological puzzles in the solar system. A strange mosaic landscape hidden beneath the clouds of Venus. and possibly the last surviving fragment of a world that no longer exists. In the next part, we will explore how these strange terrains formed and why their patterns suggest that Venus once experienced forces powerful enough to reshape an entire planet. If Tessera terrain truly represents the oldest surviving surface on Venus, then it must have formed during a very different era in the planet's history, an era when powerful geological forces were shaping the crust in ways we still struggle to understand today. To begin unraveling this mystery, scientists first studied the patterns visible in Tessera landscapes. Radar images revealed that these regions are not simply rugged or mountainous. Instead, they contain intricate networks of intersecting ridges, valleys, folds, and fractures. Some ridges run parallel across the terrain, like waves frozen in stone. Others cut across those ridges at sharp angles, creating complex geometric patterns. These intersecting structures are one of the defining features of Tessera terrain. On Earth, when geologists see multiple generations of ridges intersecting each other, it usually means the crust has experienced several episodes of deformation. In other words, the ground was not shaped by a single tectonic event. It was reshaped repeatedly over long periods of time. This is exactly what Tessera terrain appears to record. The ridges in these regions often run in 2 or even 3 different directions, suggesting that the crust was compressed from multiple angles during different stages of its geological history. That level of deformation implies something remarkable. At some point in the distant past, the crust of Venus may have been far more dynamic than it is today. Today, Venus appears geologically quiet in terms of large-scale tectonic motion. There are volcanoes and lava flows, but scientists do not see clear evidence of the moving tectonic plates that dominate Earth's geology. But Tessera terrain hints that the story may once have been very different. To understand why, we need to consider how planetary crust behaves under stress. A planet's crust is not perfectly rigid. Under the enormous forces generated by internal heat and mantle movement, the crust can bend, fracture, stretch, or compress. These forces originate deep inside the planet. Beneath the crust lies the mantle, a thick layer of hot rock that slowly circulates through convection. Hot material rises upward, cools near the surface, and then sinks again. This slow circulation transfers heat from the planet's interior toward its surface. On Earth, this process drives the movement of tectonic plates. But Venus appears to operate differently. Instead of plates sliding past one another, the crust of Venus may behave more like a single continuous shell covering the planet. This type of structure is sometimes called a stagnant lid. In a stagnant lid planet, the crust remains mostly locked in place while heat builds up beneath it. Eventually, the internal pressure may become strong enough to deform the crust in dramatic ways. Some scientists believe Tessera terrain formed during periods when the crust was being intensely compressed and stretched by mantle activity below. As hot mantle material pushed upward, it may have caused the surface to buckle and fold. Later, as the forces shifted, the crust may have been stretched in different directions, creating new fractures and ridges that intersected the older ones. Over time, these repeated episodes of deformation could have produced the complex mosaic patterns we see today. But there is another important clue hidden in the structure of Tessera terrain. Many of the ridges appear to be folded rock layers rather than simple fractures. Folding occurs when rocks are compressed slowly enough that they bend rather than break. This suggests that the crust in Tessera regions may have been thick and relatively ductile at the time these structures formed. That raises an intriguing possibility. Perhaps the crust of early Venus was thicker and more continent-like than scientists once thought. On Earth, continental crust behaves very differently from the thinner crust that forms beneath the oceans. Continents are thicker, more buoyant, and more resistant to recycling. Because of this, continental regions can preserve ancient geological structures for billions of years. Some researchers have proposed that Tessera terrain might represent something similar: fragments of ancient continental-style crust on Venus. If that idea is correct, Tessera terrain could preserve a record of geological processes that occurred very early in the planet's history, possibly even during a time when Venus was more Earth-like. But this hypothesis remains controversial. Unlike Earth, Venus has no oceans today and no clear evidence of plate tectonics. However, some models suggest that Venus may once have had liquid water on its surface billions of years ago. If water existed on Venus in the distant past, it could have influenced the planet's tectonic behavior. On Earth, water helps lubricate faults and allows tectonic plates to move more easily. Without water, the crust becomes stronger and more resistant to motion. Some scientists therefore speculate that early Venus might have briefly experienced tectonic processes more similar to Earth's before the planet's runaway greenhouse effect evaporated its oceans. If this were true, Tessera terrain might be the geological scars of that ancient tectonic era. But confirming this idea is extremely difficult because we cannot yet examine the rocks of Venus directly. Instead, scientists rely heavily on radar images collected by the spacecraft Magellan. Magellan mapped more than 98% of Venus's surface during the early 1990s, revealing the complex structure of Tessera terrain in unprecedented detail. From orbit, these regions appear brighter in radar images than the surrounding volcanic plains. This brightness occurs because rough, rugged terrain reflects radar signals more strongly than smooth surfaces. The complex ridges and valleys of Tessera terrain therefore stand out clearly in the data. By analyzing these patterns, scientists can reconstruct the sequence of events that shape the landscape. For example, if one ridge cuts across another ridge, it must have formed later. This principle allows geologists to determine the relative timing of different deformation events. In many Tessera regions, scientists have identified multiple generations of ridges, folds, and fractures. Each generation represents a different stage in the geological evolution of the crust. Some ridges appear to have formed through compression, others formed through stretching. Still others may have developed as the crust slid along deep faults. This layered history suggests that Tessera terrain formed over very long periods of time, possibly hundreds of millions of years. Another interesting feature of Tessera terrain is the presence of deep valleys between the ridges. These valleys may have formed as the crust stretched and broke apart after earlier compression. In some places, the valleys appear to be filled with volcanic material that flowed into the low areas after the terrain had already formed. This indicates that volcanic activity occurred after the major tectonic deformation, which again supports the idea that Tessera terrain is older than much of the surrounding landscape. Over time, enormous lava flows spread across Venus, covering large portions of the planet. These flows created the smoother plains that dominate the surface today. But in many areas, the lava appears to have stopped at the edges of Tessera regions, flowing around them rather than burying them completely. This suggests that Tessera terrain stood higher than the surrounding plains at the time the lava erupted. The higher elevation may have protected these ancient regions from being buried, which is why they remain visible today. But elevation alone may not explain their survival. The crust in Tessera regions may also be mechanically stronger than other parts of the planet. If the rocks there are thicker or composed of different materials, they may resist deformation and volcanic flooding more effectively. Some scientists have proposed that Tessera crust could contain higher concentrations of certain minerals that increase its strength. However, without direct samples, this idea remains speculative. Even so, Tessera terrain continues to challenge our understanding of Venus, because it suggests that the planet's geological history may be far more complicated than once believed. Rather than being a simple volcanic world resurfaced by lava, Venus may have experienced multiple tectonic eras, each era leaving behind traces in the form of folded ridges, fractured plateaus, and ancient highlands. In that sense, Tessera terrain may be the memory of an earlier Venus, a record of forces that once reshaped the planet's crust in ways we are only beginning to understand. And as scientists continue to study these strange landscapes, they may reveal not only the history of Venus, but also the processes that shape rocky planets throughout the universe. In the next part, we will explore another important question. If Tessera terrain is truly ancient, what does it tell us about the interior of Venus and the powerful forces still hidden beneath the planet's surface today? From orbit, the Tessera terrain of Venus looks like a tangled web. Ridges cross other ridges. Valleys intersect valleys. Long folded structures twist across the surface in patterns that seem almost chaotic at first glance. But to planetary geologists, these patterns are not random. They are clues. Each ridge, fracture, and fold records a moment in the distant geological history of Venus. By studying the shapes and orientations of these structures, scientists can begin to reconstruct the forces that shaped the planet billions of years ago. In many ways, Tessera terrain behaves like a giant geological archive. On Earth, geologists often study mountain belts to understand how continents collided in the past. Layers of rock are folded, fractured, and stacked on top of one another during these collisions. Over time, the mountains slowly erode, but the structural patterns remain preserved in the rocks. Something similar may have happened on Venus. When scientists examined radar images from the spacecraft Magellan, they noticed that Tessera regions often contain two dominant sets of ridges. One set might run roughly east to west, another set might run north to south. Where these ridges intersect, the surface forms a distinctive pattern that resembles woven fabric or a mosaic of broken tiles. This is where the name Tessera comes from. In ancient Roman architecture, Tesserae were the small tiles used to build mosaics. When scientists saw the intersecting ridges on Venus, the similarity was striking, but the patterns revealed something deeper. If two ridge systems intersect, it means the crust experienced two different periods of stress. First, the surface was compressed in one direction, creating the first set of ridges. Later, the direction of stress changed, producing a second set that cut across the earlier structures. This tells us that the forces shaping Venus were not constant. They shifted over time, and that means the interior of Venus must have been undergoing complex changes as heat moved through the mantle. To understand this better, imagine the crust of a planet as the thin outer shell of a slowly cooling sphere. Deep inside the planet, radioactive elements generate heat. At the same time, leftover heat from the planet's formation continues to rise toward the surface. As this heat moves upward through the mantle, it creates slow currents of circulating rock. These currents can push upward against the crust. In some places, the crust may rise and stretch. In others, it may be compressed and folded. On Earth, this movement eventually breaks the crust into tectonic plates. But Venus seems to lack this kind of plate tectonics. Instead, its crust behaves more like a continuous lid. Scientists call this a stagnant lid regime. In a stagnant lid planet, the crust does not move freely across the surface. Instead, it remains mostly locked in place while the mantle circulates beneath it. But even in this situation, the crust can still deform. If mantle currents become strong enough, they can push upward on the underside of the crust, creating stress across large regions of the surface. Over time, that stress may cause the crust to buckle, fold, and fracture. This could be exactly what happened in Tessera regions. Some scientists believe these areas formed above powerful mantle upwellings, giant plumes of hot material rising from deep inside the planet. As the plume pushed upward, it may have stretched the crust outward. Later, as the plume cooled and sank back into the mantle, the crust could have been compressed again. This cycle of stretching and compression could produce the complex intersecting ridges we observe today. But Tessera terrain reveals another important clue. Many of the ridges appear to have been heavily folded, not just fractured. Folding happens when rock layers are compressed slowly enough that they bend rather than break. This suggests that the crust of Venus may have been relatively warm and flexible at the time these structures formed. If the crust had been cold and brittle, it would have shattered instead of folding. The presence of folds therefore tells us something about the temperature and thickness of the crust during that era. It implies that Venus's crust may once have been thicker and more ductile than it is today. This is important because crust thickness affects how heat escapes from a planet. A thick crust can trap heat inside the planet, allowing pressure to build up beneath the surface. Eventually, that pressure must be released. One possible release mechanism is massive volcanic resurfacing. In fact, many scientists believe Venus experienced a global resurfacing event hundreds of millions of years ago. During this event, enormous volumes of lava may have erupted across the planet, covering vast areas of older terrain. These lava flows created the smooth volcanic plains that dominate much of Venus's surface today. But Tessera terrain appears to predate those plains. The volcanic lava often stops at the edges of Tessera regions or flows around them. This suggests that the Tessera landscapes were already present before the volcanic resurfacing occurred. In other words, Tessera terrain may represent the surviving fragments of Venus's ancient crust, fragments that escaped burial during the massive volcanic episodes that reshaped the rest of the planet. Another intriguing feature of Tessera regions is their high elevation. Many Tessera plateaus stand higher than the surrounding volcanic plains. This elevation difference may not be accidental. On Earth, high elevations often correspond to thicker crust. For example, the continental crust beneath mountain ranges can be significantly thicker than the crust beneath the oceans. If Tessera terrain represents areas where the crust is thicker, that could explain why these regions resisted volcanic flooding. The thicker crust may have remained elevated while lava filled lower regions nearby. Some researchers have even proposed that Tessera terrain might represent protocontinents on Venus. That idea remains controversial, but it highlights how unusual these regions are, because nowhere else on Venus do we see such complex geological patterns. Another clue comes from the distribution of Tessera terrain across the planet. These regions are not scattered randomly. Instead, they tend to cluster within major highland areas. One of the largest examples occurs within Ishtar Terra, a massive plateau roughly the size of Australia. Ishtar Terra contains some of the highest mountains on Venus, including the towering Maxwell Montes. Within this region, Tessera terrain forms large portions of the highland crust. The presence of Tessera structures in these highland areas suggests that the crust there experienced intense tectonic deformation long ago, possibly during a time when Venus's interior was far more active, and that raises a fascinating possibility. Perhaps Tessera terrain formed during a transitional period in Venus's evolution, a time when the planet was shifting from an earlier tectonic system to the stagnant lid regime we see today. If Venus once had something resembling plate tectonics, even briefly, the scars of that system might still be preserved in these ancient terrains. But proving that idea requires much more data, because radar images alone cannot reveal the composition of the rocks. Without knowing what minerals make up Tessera terrain, scientists cannot fully determine how these regions formed. Future missions to Venus may finally provide answers. New spacecraft equipped with advanced radar instruments will map the surface with far higher resolution than ever before. Some missions may even send landers capable of surviving the harsh environment long enough to analyze the chemistry of the rocks. If those landers reach Tessera terrain, they could provide the first direct evidence of the planet's ancient geological processes. Until then, Tessera terrain remains one of the most intriguing puzzles in planetary science. A mosaic of ridges and valleys frozen in time, a geological record of forces that once shaped the surface of Venus in ways we still struggle to understand, and perhaps the last surviving trace of a very different world hidden beneath the planet's thick and endless clouds. In the next part, we will explore another crucial mystery. If Tessera terrain truly formed billions of years ago, what does it reveal about the early climate and history of Venus itself? Today, Venus is one of the most hostile worlds in the solar system. Its surface is hotter than a kitchen oven. The pressure at ground level is crushing, thick clouds of sulfuric acid cover the entire planet, reflecting sunlight and hiding the surface beneath a permanent layer of haze. Nothing about this world seems gentle or familiar, and yet the strange landscapes of Tessera terrain hint at a time when Venus may have been very different. To understand why scientists think this, we need to imagine Venus not as the burning planet we see today, but as it might have existed billions of years ago, when the solar system was young. During that early era, Venus and Earth were remarkably similar. Both planets formed from the same region of the protoplanetary disk. Both are nearly the same size, with comparable masses and densities. Their gravitational fields are similar, and their internal structures likely developed in similar ways. For a long time, scientists believed that Venus might once have been almost identical to Earth. Perhaps it even had oceans. Perhaps it had clouds of water vapor instead of sulfuric acid. Perhaps rain once fell on its surface. If this seems surprising, it is because today Venus is the opposite of Earth in almost every way. But planetary evolution can be unpredictable. Small differences early in a planet's history can eventually lead to enormous changes over billions of years. One of the key factors in planetary climate is distance from the Sun. Venus orbits slightly closer to the Sun than Earth does. That small difference means Venus receives significantly more solar energy. Early in its history, that extra heat may have caused the planet's oceans, if they existed, to slowly evaporate. As a water vapor accumulated in the atmosphere, it created a greenhouse effect. Water vapor traps heat extremely efficiently. The more water vapor entered the atmosphere, the more heat became trapped near the surface. And the hotter the surface became, the more water evaporated. This feedback loop is known as a runaway greenhouse effect. Eventually, the process could have become unstoppable. The oceans would have completely evaporated. Without oceans, there would be no way to remove carbon dioxide from the atmosphere through weathering and rock formation. Carbon dioxide would build up, trapping even more heat. Over time, Venus transformed into the extremely hot world we see today. But if this transformation happened gradually, there may have been a long period when Venus still had a more moderate climate. And if that period existed, it might have allowed geological processes similar to those on Earth. Processes like tectonic deformation, processes that could help explain the formation of Tessera terrain. On Earth, the presence of water plays a crucial role in tectonic activity. Water weakens rock and lubricates faults, allowing tectonic plates to slide past one another. Without water, rocks become stronger and more resistant to motion. If early Venus once had oceans, those oceans could have influenced the behavior of the crust. They might have allowed tectonic plates to move more easily across the surface. Some scientists believe that Venus may have briefly experienced Earth-like tectonics early in its history. If that is true, then Tessera terrain might be the remnants of ancient tectonic belts, regions where the crust was compressed, folded, and fractured during plate collisions. Over time, as Venus lost its water and its climate became hotter, those tectonic processes may have stopped. The crust could have thickened and locked into place, forming the stagnant lid structure scientists observe today. In that case, Tessera terrain would represent the fossil record of an earlier tectonic system, a snapshot of a time when Venus may have behaved more like Earth. But there is another possibility. Even without oceans or plate tectonics, a planet can still experience powerful tectonic deformation. Internal heat can cause the mantle to rise in massive plumes, pushing against the crust from below. These mantle plumes can stretch and compress the crust in complex ways. On Earth, plume activity is responsible for volcanic hotspots such as Hawaii. On Venus, plume activity may have been even more intense. Because Venus does not have moving tectonic plates to release heat gradually, the planet's interior may build up enormous pressure over time. Eventually, that pressure must be released. One possible release mechanism is large-scale crustal deformation. Mantle plumes rising beneath the surface could cause the crust to warp and fold, creating the intersecting ridges seen in Tessera terrain. Later, as the plume weakens or shifts location, new stresses could form in different directions. This would create multiple generations of ridges and fractures crossing each other. Exactly the patterns scientists observe in radar images. Much of our knowledge about these structures comes from the detailed mapping performed by the spacecraft Magellan. Magellan's radar imaging allowed scientists to examine the surface of Venus with remarkable clarity. Instead of smooth plains, Tessera regions appeared as rugged plateaus covered in tightly packed ridges. Some ridges run for hundreds of kilometers. Others twist and branch like tangled threads. The terrain appears so complex that some scientists have compared it to crumpled fabric, as if the crust had once been squeezed and folded repeatedly. Another striking feature is the age relationship between Tessera terrain and surrounding volcanic plains. In many places, lava flows appear to have flooded low areas near Tessera regions, but the lava rarely covers the Tessera terrain itself. Instead, it flows around these regions. This indicates that the Tessera plateaus already existed before the volcanic resurfacing events that covered much of the planet, which again suggests that Tessera terrain is extremely ancient, perhaps older than most other features on Venus. The preservation of these ancient landscapes is remarkable because Venus has experienced enormous volcanic activity over its history. Many scientists believe the planet underwent a massive resurfacing event around 500 million years ago. During this event, large portions of the planet may have been covered by lava. If Tessera terrain survived that event, it must have been structurally strong or elevated enough to resist burial. That resilience may provide important clues about the composition of the crust in these regions. Some models suggest that Tessera terrain may contain silica-rich rocks similar to continental crust on Earth. If true, this would make Tessera regions chemically distinct from the basaltic volcanic plains surrounding them. However, without direct samples, this idea remains unconfirmed. Future missions may finally help answer this question. Several upcoming spacecraft missions are designed to explore Venus in much greater detail. These missions will use improved radar instruments to map the surface with far higher resolution. They may also measure gravitational and thermal properties of the crust. Such data could reveal whether Tessera regions are thicker or compositionally different from the surrounding plains. Eventually, landers might even reach the Tessera terrain itself. Although the extreme environment of Venus makes long-lived landers extremely difficult, even a short-lived mission could analyze the chemical composition of the rocks. that would provide invaluable information about how these landscapes formed. For now, Tessera terrain remains one of the most important clues to Venus's ancient history. It may represent a time when the planet's surface behaved very differently from what we observe today, a time when tectonic forces reshaped the crust, a time when the planet's climate may have been more temperate, and perhaps even a time when Venus was not yet the scorching inferno it would eventually become. In the next part, we will explore another piece of this puzzle: how scientists use the distribution and structure of Tessera terrain to reconstruct the deeper processes occurring inside Venus's mantle. To truly understand the Tessera terrain puzzle, scientists must look far deeper than the planet's surface. The ridges and valleys that form these strange landscapes are only the visible scars of forces that originate deep inside the planet. Far below the crust of Venus lies a vast region of slowly moving rock known as the Mantle. This layer makes up most of the planet's interior and behaves very differently from the rigid crust above it. Although the mantle is made of solid rock, the extreme temperatures and pressures cause it to flow slowly over geological time. The movement is extremely gradual, often only a few centimeters per year. But over millions or billions of years, these slow currents can reshape entire planets. This process is known as mantle convection. Heat generated inside the planet causes material deep within the mantle to rise upward. As it approaches the surface, the material cools and spreads sideways beneath the crust. Eventually, it sinks back down toward the planet's interior, completing the convection cycle. On Earth, these convective currents drive the motion of tectonic plates. But Venus appears to operate under a very different system. Instead of plates sliding past each other across the surface, Venus's crust seems to behave like a single, continuous shell covering the entire planet. Scientists often describe this as a stagnant lid. In a stagnant lid planet, the crust does not easily break into moving plates. Instead, it forms a thick, rigid layer that traps heat beneath it. Over time, that trapped heat builds pressure inside the mantle. Eventually, the pressure becomes strong enough to deform the crust in dramatic ways. When this happens, the surface can buckle, fracture, and fold. And this may be exactly what happened in the regions where Tessera terrain formed. One of the key clues supporting this idea comes from the distribution of Tessera terrain across Venus. These regions are not randomly scattered across the planet. Instead, they tend to occur within large highland areas that rise above the surrounding volcanic plains. These highlands include regions such as Ishtar Terra and Aphrodite Terra. Both of these areas contain extensive Tessera landscapes. Their high elevations suggest that the crust beneath them may be thicker than elsewhere on the planet. Thicker crust can behave differently under stress. It may resist volcanic flooding more effectively, allowing ancient terrain to remain exposed while surrounding areas become buried under lava. But the elevation of Tessera terrain may also reveal something about the mantle beneath these regions. Some scientists believe that Tessera terrain formed above ancient mantle upwellings, massive plumes of hot material rising from deep inside the planet. These plumes can push upward against the crust, causing it to stretch and fracture. As the plume continues to evolve, the stresses in the crust can change direction, producing additional ridges and folds that intersect the earlier structures. Over time, this repeated deformation could produce the complex patterns seen in Tessera terrain today. However, the story may be even more complicated because some Tessera regions appear to record multiple stages of deformation. Radar images collected by the spacecraft Magellan show that many Tessera ridges run in several different directions. This suggests that the crust was compressed, stretched, and reshaped multiple times. Each episode left its own set of ridges and valleys across the terrain. For planetary geologists, this layered structure is incredibly important. It means the Tessera terrain formed over long periods of geological time rather than during a single event. This prolonged deformation hints at a dynamic interior during the early history of Venus. Perhaps the mantle circulation patterns were more vigorous in the past. Perhaps the crust itself was thinner or weaker. Or perhaps Venus once had a tectonic regime that no longer exists today. Another possibility involves the cooling history of the planet. When planets first form, they contain enormous amounts of internal heat. This heat comes from both the energy released during formation and the decay of radioactive elements within the interior. Over billions of years, planets gradually lose this heat. As the interior cools, the behavior of the mantle and crust can change dramatically. In the early history of Venus, the mantle may have been hotter and more mobile. Stronger convection currents could have pushed against the crust with greater force, producing intense deformation. As the planet cooled, these processes may have slowed down. Eventually, the crust may have thickened and become more rigid, preventing further large-scale tectonic activity. If this is correct, Tessera terrain might represent a transitional phase in the evolution of Venus, a time when the planet's interior was still energetic enough to deform the crust repeatedly, but before the volcanic resurfacing events that later reshaped most of the surface. Another fascinating clue comes from the relationship between Tessera terrain and volcanic plains. Most of Venus's surface is covered by vast plains of basaltic lava. These plains are relatively smooth compared to Tessera terrain. When scientists examined radar images from Magellan, they noticed that many lava flows appeared to avoid Tessera regions. Instead of covering them, the lava often flows around the edges of the Tessera plateaus. This suggests that the Tessera terrain was already elevated and structurally complex before the lava floods occurred. In some places, the boundaries between Tessera terrain and volcanic plains are extremely sharp. The smooth lava flows stop abruptly at the edge of the rugged terrain. This implies that the Tessera crust was strong enough to resist being buried by the molten rock, which again supports the idea that these regions may have thicker or compositionally different crust. On Earth, continental crust contains more silica-rich rocks than the basaltic crust beneath the oceans. These rocks are lighter and more buoyant, allowing continents to remain elevated for billions of years. If Tessera terrain contains similar materials, it might behave in a comparable way. However, there is still no direct evidence for this. Without samples from the surface, scientists cannot confirm the chemical composition of Tessera rocks. That is why future missions to Venus are so important. New radar instruments will soon provide far more detailed maps of the surface, These maps may reveal smaller structures within Tessera terrain that were impossible to detect in earlier images. In addition, gravity measurements could help determine whether the crust beneath these regions is thicker than elsewhere on the planet. If Tessera terrain truly represents thicker crust, it would strengthen the idea that these regions form through long-term tectonic processes rather than short-lived volcanic events. But the biggest mystery remains the same. Why did these processes stop? If Venus once had a more dynamic tectonic system, what caused it to shut down? One possible answer lies in the planet's extreme climate. As the runaway greenhouse effect intensified, surface temperatures rose dramatically. Higher temperatures can change the mechanical behavior of rocks. Hotter rocks may become weaker, allowing volcanic activity to dominate instead of tectonic deformation. At the same time, the loss of water from the planet's atmosphere could have made the crust stronger and more resistant to plate motion. Without water to lubricate faults, tectonic plates might have become locked in place. This could have forced the planet into the stagnant lid regime we observe today. In that scenario, Tessera terrain would represent the final record of a vanished tectonic era, a time when Venus's crust was still capable of complex deformation, a time when the planet may have looked far more Earth-like than it does today. But the evidence remains incomplete because the surface of Venus is still hidden beneath its thick clouds. And until new missions return to explore the planet, the Tessera terrain puzzle will remain one of the most fascinating mysteries in planetary science. In the next part, we will examine another crucial piece of the puzzle: how scientists use crater counts and surface dating to estimate the true age of Tessera terrain, and what those ages reveal about the ancient history of Venus. One of the most difficult questions in planetary science is determining how old a surface really is. On Earth, geologists can analyze rock samples directly. By studying radioactive elements inside the rocks, they can calculate precise ages that often reach back billions of years. But on Venus, things are far more complicated. The extreme heat and crushing atmospheric pressure make long-lasting landers extremely difficult. Only a handful of spacecraft have ever reached the surface, and most survived for less than 2 hours. That means scientists cannot yet collect rock samples from Venus the way they do on Earth or even on the Moon. Instead, researchers must rely on indirect techniques to estimate the age of the planet's surface. One of the most important of these techniques involves impact craters. Throughout the history of the solar system, asteroids and comets have occasionally collided with planets and moons. Each impact leaves behind a crater. Over time, the number of craters on a surface gradually increases. A very old surface tends to accumulate many craters. A younger surface will have far fewer. By counting how many craters exist across a region, scientists can estimate how long that surface has been exposed. This method has been used successfully on the Moon, Mars, and Mercury. When planetary scientists first mapped the surface of Venus using radar from the spacecraft Magellan, they applied the same technique. What they discovered was surprising. Venus does have impact craters, but far fewer than expected. In total, scientists have identified roughly 1,000 craters across the entire planet, compared to heavily cratered worlds like Mercury, or the Moon, this is an extremely small number. The craters that do exist are also distributed quite evenly across the surface. There are no regions with dramatically higher crater densities. This uniform distribution suggests something unusual happened in the planet's past. Most scientists believe Venus experienced a global resurfacing event hundreds of millions of years ago. During this event, enormous volumes of lava may have erupted across the planet, covering older terrain and effectively resetting the crater record. Once the new surface cooled, impacts began accumulating again. Based on crater counts, researchers estimate that the current surface of Venus is roughly 500 to 700 million years old. In geological terms, that is relatively young. Earth's continents contain rocks more than 4 billion years old. The Moon preserves surfaces older than 3 billion years. Venus, by comparison, appears to have erased much of its early history. But Tessera terrain complicates this picture. When scientists examine crater distributions carefully, they notice something interesting. Some Tessera regions appear to contain slightly higher crater densities than the surrounding volcanic plains. This suggests that Tessera terrain may be older, perhaps significantly older. However, interpreting this data is not simple. Because Venus's thick atmosphere filters out many smaller impactors before they reach the surface. Asteroids smaller than roughly a kilometer in diameter often burn up or break apart before impact. This means Venus naturally produces fewer small craters than other planets. The atmosphere also causes many impactors to fragment as they descend. As a result, several Venusian craters appear in clusters, where fragments from a single asteroid strike the surface simultaneously. These unusual crater patterns make crater counting more complicated than on airless bodies like the Moon. Even so, crater statistics still provide valuable information, and they strongly support the idea that Tessera terrain formed before the volcanic resurfacing event. If the lava flows had buried these regions completely, the crater distribution would look very different. Instead, the Tessera plateaus remain visible above the surrounding plains. This indicates they were already present when the lava flooded much of the planet. In other words, Tessera terrain may preserve pieces of Venus's ancient crust that survived the resurfacing event. But how old are these regions really? Some scientists believe Tessera terrain could date back more than 1 billion years, possibly even earlier. If that is true, these regions may contain the oldest surviving geological record on Venus, and that makes them extremely important for understanding the planet's early evolution. Another piece of evidence supporting their ancient origin comes from tectonic relationships between Tessera terrain and surrounding structures. In many places, volcanic plains appear to fill low valleys near Tessera plateaus, but the lava rarely covers the ridged terrain itself. Instead, it flows around the edges. This suggests the Tessera landscapes were already elevated when the lava erupted. If these terrains were younger than the plains, we would expect the opposite pattern. The lava would bury them, but the radar images show the ridges clearly rising above the volcanic plains. These observations again come largely from the mapping performed by the spacecraft Magellan. Magellan's radar images allowed scientists to examine these relationships across nearly the entire planet. The mission revealed that Tessera terrain covers roughly 8% of the surface of Venus. Although this is a relatively small fraction, it represents some of the most geologically complex terrain anywhere in the solar system. And because these regions appear to be older than the surrounding plains, they may contain clues about Venus's earliest tectonic processes. But determining their true age remains difficult. Without rock samples, scientists cannot perform precise radiometric dating. Instead, they must rely on relative dating methods. These methods compare the relationships between geological structures. For example, if one ridge cuts across another ridge, the cutting ridge must be younger. Similarly, if lava flows fill a valley, the valley must have existed before the lava erupted. By studying thousands of these relationships across Tessera terrain, scientists can reconstruct the sequence of geological events. The results suggest that Tessera terrain formed through multiple stages of deformation. Each stage left its own set of ridges and fractures across the landscape. Some structures may represent early compression events. Others may record later stretching or faulting. Together, they form a layered history of crustal deformation. This history may span hundreds of millions of years, possibly longer. Another intriguing question is whether Tessera terrain formed before or after the runaway greenhouse transformation of Venus. If these terrains formed during an earlier, cooler climate, they might preserve evidence of geological processes influenced by water. Some scientists speculate that early Venus may have had shallow oceans or large bodies of water. If so, those oceans could have affected tectonic behavior in ways similar to Earth. But if Tessera terrain formed after Venus had already become extremely hot, then water likely played little role. Instead, the deformation would have been driven entirely by internal heat and mantle convection. At the moment, the evidence remains inconclusive. Both possibilities are still being explored. What scientists agree on, however, is that Tessera terrain represents one of the oldest surviving landscapes on Venus. These regions preserve geological structures that formed long before the volcanic plains reshaped the rest of the planet. In that sense, Tessera terrain acts like a window into the distant past, a glimpse of Venus as it once was. But many mysteries remain. How exactly did these terrains form? Why did the tectonic forces that created them eventually disappear? And what does their existence reveal about the deep interior of the planet? To answer those questions, scientists are now preparing for a new generation of Venus missions. These spacecraft will map the planet with far greater precision than ever before. They will measure gravity, heat flow, and surface composition. Some may even send landers capable of analyzing rocks directly. When that happens, Tessera terrain may finally reveal its secrets, and with it, we may learn the true story of how Earth's mysterious twin became the blazing world we see today. In the next part, we will explore the global resurfacing mystery of Venus and how it may be connected to the formation and survival of Tessera terrain. If Tessera terrain truly represents the oldest surviving surface on Venus, then another question immediately appears. What happened to the rest of the planet? Why do so many regions of Venus look relatively young compared to the ancient landscapes preserved within the Tessera plateaus? To answer that question, scientists had to examine the entire surface of Venus in detail. When the spacecraft Magellan began mapping the planet in the early 1990s, researchers expected to see a surface filled with impact craters, mountain ranges, and ancient geological scars stretching across billions of years. Instead, they saw something unexpected. Much of Venus's surface appeared remarkably smooth. Vast volcanic plains covered large areas of the planet. These plains stretched for thousands of kilometers and were formed by enormous lava flows that had spread across the crust. Compared with the rugged Tessera terrain, these plains looked young and relatively undisturbed. Even more surprising was the distribution of impact craters. As scientists counted craters across the planet, they realized something unusual. The number of craters was very small compared to other rocky worlds. Mercury and the Moon are covered with thousands of craters of different sizes, many of them billions of years old. But Venus had only around 1,000 known craters, and these craters were scattered evenly across the surface. There were no heavily cratered regions and no crater-free regions. This pattern suggested something extraordinary had happened in the past. At some point, the surface of Venus may have been almost completely resurfaced. In other words, massive volcanic activity may have buried older landscapes beneath thick layers of lava. If this resurfacing occurred on a global scale, it would explain why most of the planet looks relatively young. The older surfaces would have been erased. Only a few regions, such as Tessera terrain, might have survived the process. Scientists call this idea the global resurfacing hypothesis. According to this theory, Venus experienced an enormous geological event roughly 500 to 700 million years ago. During that time, huge volumes of molten rock erupted from the interior of the planet. These eruptions may have lasted for millions of years. Lava spread across the surface, filling low regions and creating the smooth plains that dominate the planet today. If such an event occurred, it would represent one of the most dramatic geological transformations in the solar system. Imagine a planet where most of the surface is suddenly buried beneath volcanic rock. Mountain ranges disappear, old craters vanish, entire landscapes are erased and replaced by new lava plains. Something like this may have happened on Venus. But if global resurfacing occurred, why did Tessera terrain survive? One possible answer lies in the elevation of these regions. Many Tessera terrains sit high above the surrounding plains. If lava flooded the lower parts of the planet, these elevated plateaus may have remained exposed. Lava would have flowed around them instead of burying them completely. Radar images from Magellan clearly show this pattern. In many places, volcanic plains appear to surround Tessera terrain, like a sea surrounding islands. The rugged ridges rise above the smoother lava fields. Another possibility is that the crust beneath Tessera terrain is thicker or stronger than elsewhere on Venus. If the crust in these regions resisted deformation and volcanic flooding, it might have acted like a barrier against lava flows. This idea has led some scientists to suggest that Tessera terrain might represent ancient continental-style crust. On Earth, continental crust is thicker and less dense than oceanic crust. Because of this, continents often remain elevated and stable for billions of years. If Tessera terrain behaves similarly, it could explain why these regions survived resurfacing events that buried other Without direct rock samples, scientists cannot yet confirm whether Tessera terrain truly contains continental-like materials. Another possibility is that Tessera terrain formed after the global resurfacing event rather than before it. In this scenario, the planet's surface would have been flooded with lava first. Later, tectonic forces could have deformed certain regions, creating the complex ridges and valleys of Tessera terrain. But most geological evidence seems to support the opposite sequence. The lava plains appear to flow around the Tessera regions, not across them. This suggests the Tessera terrain already existed when the volcanic flooding occurred. If that interpretation is correct, Tessera landscapes may preserve the oldest surviving geological record on Venus. But the resurfacing mystery raises another important question. What could cause such a dramatic global event? Why would Venus suddenly release enormous amounts of lava across the planet? The answer may lie deep inside the mantle. Because Venus does not have plate tectonics like Earth, heat escaping from the interior may accumulate beneath the crust. Over millions of years, this trapped heat could build enormous pressure. Eventually, the pressure might become strong enough to break through the crust. When that happens, magma from deep within the planet could erupt across vast regions of the surface. Some scientists describe this process as a planet-wide volcanic pulse. Instead of steady volcanic activity occurring continuously, the planet might experience long quiet periods followed by massive bursts of volcanism. During one of these bursts, large portions of the surface could be resurfaced in a relatively short geological time. This model fits well with the crater data observed on Venus, because if the surface had been resurfaced gradually over billions of years, we would expect to see areas with many old craters and areas with fewer craters. But Venus does not show this pattern. Instead, the craters appear evenly distributed across the surface, which suggests most of the planet's surface formed during roughly the same period. However, the global resurfacing hypothesis is not universally accepted. Some scientists argue that volcanic activity on Venus may have occurred more gradually. Rather than a single catastrophic event, the planet might have experienced many smaller eruptions spread out over time. In this gradual model, lava flows slowly covered older surfaces in different regions. Over millions of years, the result would still be a relatively young-looking surface, but without requiring a single dramatic event. Distinguishing between these models is difficult, because the thick atmosphere of Venus prevents detailed observations of the surface using traditional optical instruments. Most of our data still comes from radar imaging. Even so, the patterns revealed by the Magellan mission remain one of the strongest clues to Venus's geological history. They show a world shaped by enormous volcanic forces, a world where ancient terrains like Tessera plateaus survived while vast regions were buried beneath lava, and a world that may still be geologically active today. In fact, some recent studies suggest that Venus may still have active volcanoes. Changes detected in radar data hint that lava flows may have occurred in the relatively recent past. If this is true, it means Venus may still be releasing heat from its interior. The processes that shaped the planet long ago may not be entirely finished, but the most important mystery remains unresolved. What exactly happened during the early history of Venus? Did the planet once have oceans? Did it once have plate tectonics? Did tessera terrain form during that ancient era? Or were these landscapes created entirely by mantle-driven deformation under the stagnant lid we see today? These questions continue to drive new research and future missions. Because hidden beneath the clouds of Venus lies a geological record unlike any other in the solar system. A record that may reveal not only the history of Venus, but also the fate of rocky planets throughout the universe. In the next part, we will explore how new spacecraft missions and future technologies may finally solve the tessera terrain puzzle. For decades, the surface of Venus has remained one of the most mysterious landscapes in the solar system. Scientists know that the planet hides volcanoes, mountains, lava plains, and the strange ridged plateaus known as tessera terrain. But despite everything that has been learned, many of the most important questions remain unanswered. How exactly did tessera terrain form? What forces shaped the intersecting ridges and valleys that cross these ancient landscapes? And perhaps most importantly, what do these regions reveal about the early history of Venus itself? For a long time, researchers had very limited data with which to answer these questions. Most of what we know about the surface of Venus comes from a single mission: the radar mapping performed by the spacecraft Magellan during the early 1990s. Magellan was revolutionary for its time. It mapped more than 98% of the planet's surface, revealing the volcanic plains, massive mountain ranges, and complex tectonic structures hidden beneath Venus's thick clouds. But the technology used during that mission was limited compared with modern instruments. The radar images produced by Magellan have a resolution of roughly 100 meters per pixel. While that was extraordinary for its era, many geological details are still too small to detect at that scale. For scientists trying to understand complex structures like tessera terrain, higher resolution data is essential. Small fractures, subtle folds, and layered deformation patterns could reveal the sequence of tectonic events that shape the crust. Without seeing these smaller structures clearly, scientists must rely heavily on interpretation and modeling. That is why planetary researchers have been pushing for new Venus missions for many years. And finally, after decades of waiting, several new spacecraft are now being planned to return to the planet. One of the most important upcoming missions is Veritas. The name stands for Venus Emissivity, Radio Science, INSAR, Topography, and Spectroscopy. Veritas will orbit Venus and use advanced radar systems to map the planet's surface with far greater detail than Magellan ever could. Its radar imaging will be able to detect changes in elevation of only a few meters. This will allow scientists to produce extremely precise topographic maps of Venus. For tessera terrain, this is incredibly important. Detailed elevation data will reveal how the ridges and valleys are arranged in three-dimensional space. Scientists will be able to determine whether certain ridges form through compression, stretching, or faulting. They will also be able to measure how thick the crust might be beneath tessera plateaus. Another major mission is Envision, which will be launched by the European Space Agency. Like Veritas, Envision will use radar to map the surface of Venus with exceptional precision. But it will also carry instruments designed to analyze the chemical composition of the surface. This is especially important for Tessera terrain. If scientists can determine what minerals make up these regions, they may be able to confirm whether Tessera crust is different from the basaltic volcanic plains surrounding it. For example, if Tessera terrain contains rocks rich in silica, it might indicate the presence of continental-style crust. Such a discovery would transform our understanding of Venus, because continental crust typically forms through long periods of tectonic activity. Finding such crust on Venus would suggest that the planet once experienced geological processes far more similar to Earth than previously believed. Another exciting mission will focus on the atmosphere of Venus, but it may still provide clues about the planet's past. NASA's Da Vinci mission will send a probe directly through the thick Venusian atmosphere. As the probe descends toward the surface, it will measure the composition of the atmosphere in extraordinary detail. Certain gases in the atmosphere may preserve clues about the planet's ancient climate. For example, the ratio of hydrogen isotopes can reveal whether Venus once had large amounts of water. If scientists find evidence that Venus once had oceans, it would strengthen the idea that the planet may have experienced tectonic processes influenced by water. Such processes could help explain the formation of Tessera terrain. Although Da Vinci's probe will land in a relatively smooth region of Venus, rather than directly on Tessera terrain, its measurements could still provide critical context for understanding the planet's geological history. But orbiters and atmospheric probes are only part of the story. Ultimately, the most valuable information would come from direct surface exploration. Unfortunately, landing on Venus is extremely challenging. The planet's surface temperature of around 465 degrees Celsius can melt lead. The atmospheric pressure is crushing, and the thick atmosphere makes communication with orbiting spacecraft difficult. Past Soviet landers, such as the Venera 13, survived only a short time before failing under these extreme conditions. Even so, during those brief moments, they transmitted photographs and chemical data from the surface. Future missions may build on this success. Engineers are developing new technologies designed to survive longer on Venus. Some concepts involve electronics, made from materials capable of operating at extremely high temperatures. Others involve landers that rely on mechanical systems rather than traditional electronics. If such technology becomes practical, future missions could remain active on the surface for days or even weeks. A lander placed directly on Tessera terrain could analyze the chemical composition of the rocks. It could measure their density, mineral structure, and age. These measurements could finally reveal whether Tessera terrain represents ancient continental crust, volcanic formations, or something entirely different. Another possibility involves aerial exploration. The atmosphere of Venus, although hostile near the surface, becomes far more temperate at higher altitudes. About 50 kilometers above the ground, temperatures and pressures are surprisingly similar to those on Earth. Some scientists have proposed sending floating balloons or aerial drones to explore Venus from within its atmosphere. These vehicles could remain in the upper atmosphere for long periods while using radar to scan the surface below. Such missions could provide extremely detailed maps of Tessera terrain and other geological structures. And because they could remain operational for months, they might observe changes on the surface over time. This raises another intriguing question. Is Venus still geologically active today? For many years, scientists assumed that Venus was largely dormant, but recent studies suggest that this may not be the case. Careful analysis of radar images has revealed hints that volcanic activity may still occur on the planet. In fact, some researchers believe that lava flows may have erupted within the past few decades. If Venus is still volcanically active, it means the planet's interior continues to release heat. And if the mantle is still active, the forces that once shaped Tessera terrain may still be operating beneath the crust. Future missions may detect subtle movements in the surface caused by ongoing tectonic activity. Even tiny changes in elevation could reveal whether the crust is still deforming. Such discoveries would dramatically change our understanding of Venus. Rather than being a static world frozen in time, Venus might be a planet where geological processes are still unfolding, and Tessera terrain might represent only one chapter in a much longer story. For now, the puzzle remains unsolved. The ridges and valleys of Tessera terrain continue to hint at ancient forces that reshaped the planet long ago. But the true origin of these landscapes remains hidden beneath the thick clouds of Venus. Only with new missions and better data will scientists finally begin to understand the story written in these strange and beautiful terrains. And when that story is finally revealed, it may change the way we think not only about Venus, but about the evolution of rocky planets throughout the universe. In the final part, we will explore the larger cosmic implications of the Tessera terrain puzzle and what it may teach us about Earth, Venus, and distant Earth-like planets beyond our solar system. The strange landscapes of Tessera terrain are more than just geological curiosities. They may represent one of the most important clues scientists have about how rocky planets evolve over billions of years. Because Venus is not just another planet in the solar system. It is Earth's closest planetary sibling. The two planets are remarkably similar in size, mass, and overall composition. When scientists compare their internal structures, the similarities are striking. Both planets likely formed from the same materials in the early solar system. Both developed iron cores, thick mantles, and rocky crusts. And yet today, the two worlds could not be more different. Earth is covered with oceans, continents, and a dynamic system of tectonic plates that constantly reshape the surface. Venus, on the other hand, is a world of crushing heat and thick clouds where the surface remains hidden beneath a dense atmosphere of carbon dioxide and sulfuric acid. Understanding why these two planets followed such different evolutionary paths is one of the most fascinating questions in planetary science. And Tessera terrain may hold part of the answer, because these ancient landscapes appear to preserve a record of geological processes that occurred early in the history of Venus, processes that may have been very different from what we observe on the planet today. If Tessera terrain formed during an earlier tectonic regime, then Venus may once have experienced a period of complex crustal deformation similar to what we see on Earth. The intersecting ridges and folded structures suggest that the crust was compressed and stretched multiple times. Such deformation requires powerful forces acting beneath the surface. These forces likely originated in the planet's mantle, Deep within Venus, the mantle continues to slowly circulate through convection. Hot material rises from deeper layers, spreads beneath the crust, and eventually sinks again as it cools. This movement transfers heat from the planet's interior toward the surface. On Earth, mantle convection drives plate tectonics, but on Venus, the crust appears to form a continuous outer shell that does not break into moving plates. Instead, the planet seems to operate under what scientists call a stagnant lid regime. In this system, the crust remains mostly fixed, while mantle convection occurs beneath it. Heat builds up below the rigid crust until it eventually escapes through volcanic eruptions or tectonic deformation. Tessera terrain may represent one of the ways that Venus released this trapped heat in the past. The complex ridges and valleys suggest that the crust experienced repeated cycles of compression and extension. These cycles could have been triggered by mantle plumes rising beneath the surface. A mantle plume is a massive column of hot rock rising from deep inside the planet. When such a plume reaches the base of the crust, it pushes upward, creating enormous stress within the overlying rocks. The crust may stretch and fracture as it rises. Later, as the plume cools or shifts position, the stresses in the crust change direction. The result is a series of intersecting ridges and folds that record the changing forces acting on the surface. Over long periods of time, these processes could produce the mosaic-like patterns that define tessera terrain. But tessera landscapes may reveal even more than just the tectonic history of Venus. They may also provide clues about the thermal evolution of the planet. All rocky planets begin their lives extremely hot. During formation, enormous amounts of energy are released as material collides and accumulates to build the growing planet. Radioactive elements within the planet's interior also produce heat as they decay. Over time, this heat slowly escapes into space. The rate at which a planet loses heat can determine how its surface evolves. On Earth, plate tectonics helps release heat gradually. The movement of plates allows hot mantle material to rise along mid-ocean ridges, while colder crust sinks back into the mantle at subduction zones. This continuous recycling of crust keeps Earth's interior relatively stable. Venus lacks this mechanism. Without moving plates, heat may accumulate beneath the crust until it is released in dramatic bursts of volcanic activity. Some scientists believe that Venus may undergo cyclical resurfacing events. During these events, enormous amounts of lava erupt across the surface, covering older terrain. This process could explain why most of the planet appears geologically young. If such an event occurred roughly 500 to 700 million years ago, it might have buried much of Venus's ancient surface. Only a few regions, such as tessera terrain, may have survived. These regions may therefore represent the last remaining fragments of Venus's early crust, fragments that escaped the massive volcanic floods that reshaped the planet. But if tessera terrain truly represents ancient crust, it raises another intriguing possibility. Perhaps early Venus once had tectonic behavior more similar to Earth. Some planetary models suggest that Venus may have had liquid water on its surface billions of years ago. If oceans existed on early Venus, they could have influenced the mechanical properties of the crust. Water weakens rocks and allows tectonic plates to move more easily. Without water, rocks become stronger and more resistant to deformation. If Venus lost its water early in its history, its tectonic system might have gradually shut down. The crust would thicken and lock into place, preventing the movement of plates. The planet would transition into the stagnant lid regime we observe today. If this scenario is correct, Tessera terrain could represent the geological scars of that transition, evidence of an ancient tectonic system that no longer exists. But confirming this idea requires far more data. Most of our current understanding comes from radar observations collected by the spacecraft Magellan. Magellan provided the first detailed maps of Venus's surface, revealing the extraordinary complexity of Tessera terrain. Yet many of the finer details remain unresolved. Future missions equipped with advanced radar and spectroscopic instruments will provide far more precise measurements. These missions may reveal whether the crust beneath Tessera terrain is thicker or chemically different from the surrounding plains. If Tessera regions contain silica-rich rocks similar to Earth's continental crust, it would suggest that Venus once experienced geological processes capable of producing such materials. That discovery would fundamentally change our understanding of the planet. Because continental crust usually forms through long-term tectonic activity involving water and melting processes within the mantle. Finding such crust on Venus would imply a far more complex geological history than previously imagined. The implications would extend far beyond Venus itself, because Venus-like planets are extremely common in the universe. Many exoplanets discovered around other stars are similar in size and composition to Venus. Understanding how Venus evolved could help scientists predict the behavior of those distant worlds. If planets similar to Earth can evolve into extreme greenhouse worlds like Venus, it would reveal how fragile planetary climates can be. But Tessera terrain also reminds us that planets are dynamic systems. Their surfaces record the forces that shape them over billions of years. The ridges and valleys of Tessera landscapes are not random. They are the result of deep planetary processes that unfolded over immense timescales. Processes that may have once transformed Venus into a world very different from the one we see today. In that sense, Tessera terrain represents more than a geological puzzle. It represents a window into the evolution of rocky planets. By studying these ancient terrains, scientists may learn why some planets remain habitable while others become hostile infernos. They may learn how tectonics, atmosphere, and internal heat interact to shape the fate of worlds. And they may gain insights that help us understand our own planet's future. Because the story of Venus is not just about another world in the solar system. It is a story about how planets change, how climates evolve, and how fragile the balance of a planetary environment can be. In the final part, we will bring together everything scientists have learned about Tessera terrain and explore the deeper implications of this mystery for the future exploration of Venus. High above the blazing surface of Venus, thick clouds hide a world that still refuses to reveal all of its secrets. Beneath those clouds lies a landscape shaped by forces that have been acting for billions of years. Volcanoes have flooded vast plains with lava. Massive mountain ranges rise above the surrounding terrain. And scattered across the planet are the strange, complex plateaus known as Tessera terrain. These regions remain one of the most intriguing mysteries in planetary science. because Tessera terrain appears to preserve the oldest surviving record of geological activity on Venus. While most of the planet's surface was likely resurfaced by enormous volcanic eruptions hundreds of millions of years ago, Tessera regions somehow survived. They remain elevated, fractured, and deeply folded, like ancient pages in a planetary history book that has otherwise been erased. Over the past several decades, scientists have studied these landscapes using radar data from the spacecraft Magellan. Magellan revealed the remarkable complexity of Tessera terrain. From orbit, these regions appear as mosaics of intersecting ridges and valleys. Some ridges run for hundreds of kilometers, crossing one another at sharp angles. Others curve and twist like folded fabric. The patterns suggest that the crust in these regions experience multiple phases of deformation. At different times, the crust was squeezed, stretched, and fractured as forces deep within the planet reshaped the surface. But the precise origin of these forces remains uncertain. Some scientists believe Tessera terrain formed when mantle plumes pushed upward beneath the crust, causing it to buckle and fold. Others suggest the ridges record ancient tectonic processes that may have resembled plate tectonics on Earth. There is even a possibility that Tessera terrain formed during a transitional period in the planet's evolution, when Venus was shifting from an early tectonic regime to the stagnant lid system that dominates today. Each of these explanations could account for some of the structures observed in Tessera terrain. But none of them fully explains all of the features scientists see in radar images. And that is why the Tessera puzzle remains unsolved. One reason the mystery persists is the extreme difficulty of exploring Venus directly. The surface environment is one of the most hostile anywhere in the solar system. Temperatures reach around 465 degrees Celsius, hot enough to melt many metals. The atmospheric pressure is equivalent to being nearly a kilometer beneath the ocean on Earth. Electronics fail quickly under these conditions. Even the most advanced landers sent to Venus in the past survived only short periods. One of the most successful examples was the Soviet spacecraft Venera 13, which managed to transmit images and chemical data from the surface before the harsh environment eventually destroyed it. But despite these challenges, new technologies are now being developed that could allow scientists to explore Venus in much greater detail. Future orbiters will map the surface with radar instruments far more advanced than those used during the Magellan mission. These instruments will provide sharper images of the surface, revealing smaller fractures and folds within Tessera terrain. They will also measure the topography of the planet with unprecedented accuracy. Understanding the three-dimensional structure of Tessera regions is crucial. Elevation data could reveal whether these plateaus are supported by thicker crust or by deeper mantle structures beneath them. In addition to mapping the terrain, upcoming missions will attempt to analyze the chemical composition of Venus's surface. If Tessera terrain contains minerals that differ significantly from those found in the volcanic plains, it would suggest that these regions formed through unique geological processes. For example, if Tessera rocks contain high concentrations of silica, they might resemble continental crust on Earth. Such a discovery would be extraordinary. because continental crust usually forms through complex tectonic processes involving melting, recycling of crustal material, and the presence of water. Finding similar rocks on Venus would imply that the planet once experienced geological processes very different from those operating today. But even without direct samples, scientists continue to refine their understanding of Tessera terrain through computer modeling and improved analysis of radar data. Some models suggest that mantle convection beneath Venus may operate in large, slowly moving cells. These cells could create zones of compression and stretching in the crust above them. Over long periods of time, these stresses could generate the intersecting ridges characteristic of Tessera landscapes. Other models explore how the planet's cooling history might influence the behavior of the crust. As Venus gradually lost heat from its interior, the mantle convection patterns may have changed. These changes could alter the stresses acting on the crust, producing new generations of ridges and fractures. In this way, Tessera terrain may record a long sequence of tectonic episodes rather than a single event. Each ridge might represent a chapter in the geological evolution of the planet. Taken together, they form a complex story that spans hundreds of millions, perhaps billions, of years. Another fascinating possibility is that Tessera terrain may represent fragments of an ancient protocontinental crust. If early Venus once had oceans or large quantities of surface water, the crust might have evolved in ways similar to Earth. Water influences how rocks melt, how minerals form, and how tectonic plates move. If Venus lost its water early in its history, the tectonic system might have gradually shut down. The crust would become thicker and stronger, plate motion would cease, and the planet would transition into the stagnant lid regime observed today. If that scenario is correct, Tessera terrain could represent the final traces of that earlier tectonic system, a fossil record of a world that no longer exists. But even if Venus never had oceans or plate tectonics, the Tessera puzzle remains just as important, because understanding how these terrains formed helps scientists understand how rocky planets release internal heat. All planets must find ways to release the heat trapped inside them. On Earth, plate tectonics plays that role. On Venus, the process appears to involve massive volcanic eruptions and large-scale deformation of the crust. Studying Tessera terrain helps scientists understand how that system works, and that knowledge extends far beyond our own solar system. In recent years, astronomers have discovered thousands of planets orbiting other stars. Many of these worlds are similar in size and composition to Earth and Venus. Some may have climates similar to Earth. Others may resemble Venus, hot, hostile worlds wrapped in thick atmospheres. Understanding why Venus evolved so differently from Earth could help scientists determine which distant planets might be habitable. In that sense, the Tessera terrain puzzle is not just about Venus. It is about understanding the broader processes that shape rocky planets everywhere. The ridges and valleys of Tessera terrain are silent witnesses to a long and complicated history. They record the forces that shaped the crust of Venus long before humans ever observed the planet. And although the details of that history remain uncertain, each new mission brings us closer to solving the puzzle. One day, future spacecraft may land directly on a Tessera plateau. They may analyze the rocks beneath their feet, and reveal the minerals that formed billions of years ago. They may confirm whether these regions are remnants of ancient continents, volcanic formations, or something entirely different. When that day comes, the mosaic patterns of Tessera terrain may finally reveal their full story. Until then, the puzzle remains, hidden beneath the clouds of Venus, a reminder that even the brightest planet in our sky still holds mysteries waiting to be uncovered. And somewhere beneath those clouds, the ancient ridges of Tessera terrain continue to preserve the silent history of a world that has changed forever.